Welcome back to Machine Translation. In today's lecture, we look at computer-aided translation. So this is basically figuring out how to build tools that help human professional translators to be more productive in their work. So let's just take a big picture view of machine translation. What is actually the purpose of machine translation? This can be categorized into three major categories. The first one is assimilation. So this is the idea that the reader of the machine translation output initiates the translation and wants to know content. So say you're coming across a foreign language web page, you don't know what it says, you click on a button, Google Translate or whatever gives you the machine translation. So you're the one who actually triggers machine translation. So you're also somewhat tolerant of inferior quality. You know that you're using machine translation. And in a way, this has been the focus of major research. So the main goal is learning more about content that is encoded in foreign languages. Another one would be communication, where you want to talk to someone who doesn't speak any of the languages you know, and you still want to communicate. So you don't speak the same language and you rely on translation to bridge that communication device. So one advantage of that situation is that if something goes wrong in the machine translation, users can ask questions. So this exists in chat room translations, handheld devices, and there's also increasing interest of combining this with speech recognition. And then finally, there's dissemination. So this is when a publisher wants to make content available in other languages. Here, the reader of that material is not aware that this is translated, maybe even. I think it's written for him in his language. And of course, there's high demands for quality. So if you get a refrigerator manual and all the text is clumsy English or whatever, and it doesn't make any sense, you're probably a bit upset about that. So this is work that is currently almost exclusively done by human translators. So this is what I want to talk about today. So since this is a quality bar that automatic machine translation cannot accomplish at the moment, what can we do that? So if you can't beat human translators, why don't we join them and work more productively together? So the goal here is helping human translators. So how can machine translation help human translators? So the first thing that comes to mind, and obviously the first thing that has been also more broadly, most widely used still up till the moment, is post-editing machine translation. This is a fairly old study from Autodesk. I think it's about 10 years old, which has a nice illustration where they build machine translation system on their own data. These are so they do software, CAD software, and they build a machine translation system on their own data, then had translators post-edit the machine translation, so these are the green bars, or they had that translators just translate the material from scratch. And here they show the productivity increases. So they don't say exactly what the bar here is, but it's probably something like how many words per hour can a translator translate. That's a fairly common metric in professional translation, and typical numbers there, maybe 500 words per hour, maybe 1,000 words per hour. It depends a lot on the material and the language, obviously, as you can also see here. And they show that, yeah, throughout all these languages, and this is like 10 years ago, translators were much more productive, and it kind of tracks what our understanding is of machine translation quality. So we generally assume French machine translation quality is pretty good, and that's also where they got the biggest improvement, while we also know that Japanese and Chinese is just a much harder language pair to work with, and the improvements were lesser there. Here's an example of, we wanted to find out a little bit more of how MT quality and productivity are related. So here's an example of a study that we did where we just said, what if we give machine translation of different quality translators, how does it impact their productivity? So what we did here, we built 9 different machine translation systems. So the first one, we just trained a machine translation system on all the data we had. And this is the blue score we got. So this is about 385 million words worth of parallel data. It's Spanish English. This is actually still a phrase-based system. And then we just reduced the amount of training data by just halving it each time. And this gave us additional systems. So you see the data kind of cuts down in half each point. The last one is really very little. And the blue score is also not very great. So we train these systems on this amount of data, and we get systems of different quality, and then let human translators post-edit output from these machine translation systems. So one thing we measured then is how fast are they? Do they get still productivity improvements when they post-edited this output? So with the best system that we gave them, they spend about 4 seconds per word translating. And with the worst system, they take about 5 seconds per word translating. So this gives us a nice correlation between machine translation quality and productivity. Here's the whole thing showed in a chart. So here is the machine translation quality as measured by the blue score. So this is our best system trained on all the data. This is our worst system trained on the least data. And then we have the average post-editing speed, how many seconds they spent on a word. And yeah, it's somewhat a noisy chart, but still it's a pretty clear line here. So you basically get kind of, you can see a correlation here expressed in this line. So here is the take-home message. So if you have a machine translation system that is 1 blue point better, you decrease machine translation post-editing time by about 0.2 seconds per word, or 3 to 4%. So that's kind of the handy rule we wanted to end up with in this study. And obviously it depends on all the language pairs, and maybe if machine translation gets better and better and blue points increase, maybe it doesn't have that much impact anymore, and so on. But it's nice to see this correlation. So better machine translation gives higher productivity. This is also kind of a really good motivation to build increasingly better machine translation systems. Why, if they are good enough with several purposes, well, here we show, yeah, even if they're good enough for several purposes, if you would to make them even better, you would actually see even more productivity gains. So 3 to 4% might not look like a lot, but this is an industry where billions of dollars are spent every year. So 3 to 4% of that is quite a bit. So better machine translation quality gives us faster translations, but does it also give us better quality? So we are especially concerned if translators are faster, are they actually going to be more sloppy and make more mistakes? But it turns out the opposite is the case. So with the better machine translation systems, translators are not only faster, they also produce less mistakes. So what we're plotting here is a human evaluation of the edited machine translation output. So someone actually double checks the professional post-editor by saying how many mistakes do they make. So this uses a very specific quality metric, and here is the fail-pass ratio there. Okay, so a higher is worse, so we don't want to have too many failures. So we're going to plot this here against the post-editing speed. So here's our best system, where it took only about just over 4 seconds per word, and here's our worst system, where it took over 5 seconds per word. And there are also much more mistakes being made in the worst system than in the best system. And the other systems somewhat correlate along the lines. You do see as here, for instance, the systems are a little bit out of order. So MT2 was a system where translators were somewhat slower than with MT5. but they also made more mistakes. Um, so it's not quite how we would expect it. So they don't quite line up as expected. Okay. So one interesting, or well, should I say annoying fact about doing all these studies is that you have to deal with professional translators and you measure their speed. And what always comes up is that different translators are just very, very different from each other. And some are just fast and some of them slow. So you have to be very careful in your study design that you don't measure different translator speeds, but you don't measure the underlying um, impact of your technology. So here is here's our 9 translators. They were given an equal amount of output to be edited from each of these different machine translation systems. So they all had like the same kind of quality of MT to work with, but they have different, quite different post-editing speeds. So here's the fastest translator. So before we talked about a range between 4 to 5 seconds per word. Now this one is actually much, much faster than all that. And this is our slowest translator that spends over 6 seconds per word translating. So this is a much bigger difference than the difference of that is impacted by our technology. In terms of quality, generally not a very strong correlation between translator speed and mistakes. So here, yeah, he does probably make the fastest translator makes a little bit over average number of mistakes, but these numbers are pretty close. For instance, the slowest translator here makes 18 mistakes. He's actually worse than the one that is between the two and is actually the best translator in terms of failures. Speed is somewhat here. Another way to measure post-editing effort, what is often done is edit rate. How much do they actually change? And obviously there's some correlation between speed and edit rate. So the fastest translator here changes only about 2.78 words, but the slowest translator also doesn't change much, while other translators that are relatively slow do change quite a lot. So slow translator might be also more diligent. Translation is a bit of a task where you never quite have it 100% perfect, so you can fiddle with things and try to improve them. However, if you're paid per word, you're only going to do this up to a certain point. Okay, so the big take-home message here is basically this difference here between individual performance of translators. So this makes a lot of these studies very difficult because you have to have a large variance to deal with. So you need to have a large number of participants in the study, and they have to do a significant amount of work so you actually see any kind of signal. And a cynical take on this might also be maybe you shouldn't worry about the technology. Maybe you should just hire translator 6 and you're fine. Okay, let's look at now some methods to improve the collaboration between machine translation systems and professional human translators. So how do we improve the man-machine interaction here? Here's an overview of various kind of things I'm going to go over. So we'll start with interactivity. So the traditional professional translator approaches are either you translate from scratch, that's obviously you don't use any of the technology. We already talked about post-editing machine translation output. Another method that is very common by professional translators is post-editing translation memory match. I have to explain that a little bit. So already since the 90s, the technologies are in place where when a translator works on translating a document, they have cut tools, computer-aided translation tools, that retrieve sentences that are very similar to the sentences that are currently translated. This makes a lot of sense if translators kind of translate same kind of material, maybe it's a new product manual from one that was already translated. Maybe just yearly in the extreme case, maybe they just, now translate an edited version of a document that they already translated yesterday. So if they already translated sentence, the post-editing the translation memory tool retrieves these old sentences that they already translated. This gets shown to the translator, and then they can add it. It not only returns perfect matches, it also returns so-called fuzzy matches, so sentences that are quite similar to what you currently translate, maybe just the product name change, otherwise the same sentence, and then they can only edit the mismatch. So our question here is, besides these traditional professional translator approaches, are there more interactive collaboration between machine and professional possible? So here is a method that kind of is about 20 years old, was proposed in a tool called TransType, and that we also here at Hopkins have done work on. So here's the idea. So this is the sentence in German. Hat seit Monaten geplant, im November einen Vortrag in Baltimore zu halten. Okay, who knows what that means? But the professional translator basically would now sit here, and here's his cursor prompt, and start translating. Except this is now interactive machine translation, and the tool basically suggests what the next word is. So the tool might suggest he. And then the translator says, yeah, that's fine. Presses tab, accepts it, and then tool makes a new suggestion. So what's happening here is essentially that the machine translation that was generated for the sentence is fed word by word to the translator. So here now the tool suggests 4 months, which is a translation of this phrase here. But here the translator now suddenly says, hey, wait, no, I actually don't like where any of this is going. And I'm actually going to change this word here to planned. And now we can't feed the translator the machine translation anymore. We now basically have to figure out how can we continue this, what is being called a prefix. How can we continue this in a way that it makes sense? So this is now the challenge we have to deal. How can we predict the next word given a so-called prefix? So let's say here now our tool also produces 4 months, and then the user can accept that or not. Here's actually one visualization of this tool that we built. So it actually shows more than one word. It actually shows here 3 words. And it highlights the next word. So if you press tab here, it would accept this word here. There are also other examples like showing the rest of the sentence. So there's a lot of options about how do you actually build this into user interface. A big problem of building these computer-aided translation tools is the user interface. What information do you show that? If you kind of get excited about this whole idea about, oh yeah, the machine translation system, probabilities, numbers, alternatives, there's so much information we could show the human translators, it's very easy to overwhelm them with stuff. Let's look at some of the tools that have been built around this idea. Here's one from a company called Lilt. That company actually still exists, and they're still working on this kind of tool. I think they had that as a product for a while. I think at the moment they use it mostly internally, but who knows where this is going. So basically the same idea. You have here a French input sentence, and you translate it, and this is what the translator already committed to. In gray here is the completion of the sentence all the way to the end. And then the translator here has shown multiple alternatives, and then they can pick one of them. Here's another additional information that can be shown, which is how confident the tool is about these different words. So all these are, you can imagine, and we'll get into how to actually compute this. You can imagine these are things that can be shown to the translator. At some point, the question is this a way to cluttered user interface that confuses the user? That's a pretty open question. Okay, let's go into how interactive prediction works. First, you work with something you're familiar with from early homeworks with a search graph. So you have the decoder that decodes a sentence, it considers all the different translation options, and kind of comes up with a translation. So while it comes up with a translation, such as he has 4 months and so on, it also, at any given point, it also considered additional options how to continue to translate. And we discussed, when we discussed recombination in search, that sometimes we can say, well, these are indistinguishable paths, so we can actually throw out. So previously we just argued for throwing out this sentence. Now we actually connect it up to why we can throw it out, because it ends up also at this point here. So this has a big benefit of not just having a fixed number of alternative translations defined by the final hypothesis. This is actually a full stretched out lattice with all kinds of different paths in it. So the idea is we can search this graph against what the user typed in. So initially, our model would just predict kind of the mainline best path through this lattice. So this is the optimal path through the lattice. This is what the translator would be fed. So the translator would be fed first this word, then that word, then that word, then that word. So if the translator, however, decides that they want to start with he planned, then, oh yeah, that's in our graph too. It's not our best path, but it's also in our graph. So we now gonna continue from there, the best continuation. So you find the best path in the graph that is constrained by this prefix, but otherwise has the highest probability. This method works as long as what the translator typed in is actually in the graph. If what the translator types in is not in the graph anymore, that's a problem. So what can we do then? So let's say the translator types in something like he wanted 4 months. That's not in there, but we can basically find 2 possible paths. This is one here that only differs by this word, and here is another path that also differs by this word. So we can find minimum edit paths. We can find minimum edit paths, meaning paths that are only changed by the minimum number of edits. So both of these paths only changed by one word. And among the ones with the same minimum number of edits, we can find the most probable path and just basically then continue from there. So a match that allows edits will also match this input up to here, but having one edit. However, searching through a lattice with a certain number of edits definitely has a problem of being slower. Here is a runtime analysis of this method of matching against the graph that shows, first of all, the length of the prefix. So this is down here. So the prefix, what the user already typed in is 5, 10, 15, 20. So this is what we have to match against the lattice. And then different colors is shown here, how many edits are there between the prefix and the lattice. What's the minimum number of edits? So if there's 0 edits, the prefix actually is in the lattice. 1 edit, there's 1 word that has to be changed to match the lattice, and so on and so on. So you see here, the more edits there are, the harder it is to match the graph. Okay, let's look at some more kind of features to make this maybe a bit more interesting. So one is word alignment visualization. So let's say you're somewhere here in the middle of a sentence. So this is a sentence you want to translate. This is where you are. And now the system proposes to translate in, and you're like, why in? So it might be interesting to show the translator, hey, I'm proposing to translate the word in because that is the word in the input that I think you should translate next. So we can highlight the word alignment between the next word and the word in the input sentence. Another thing we could illustrate is what you have already translated. So here is the translation, and all the stuff in gray here is matching what is in this prefix. So we translated all the stuff in gray already, and now we have to, the next thing we want to translate is that the system suggests us to translate is the word im as in. So this makes it then visually much clearer about where you are, what you have to do, what's going on. So how can we do this? So this is actually pretty straightforward. You could view word alignments as a byproduct of the matching against the search graph, because you matched against the search graph, and you know where the search graph was generated from. So that is aligned with the input sentence, so you can match it against that. Or what you could also do is just to run the kind of word alignment methods that we discussed at the very beginning, these IBM Model 1 type word alignment methods that figuring out correspondence between inputs and outputs words. So if you feed it the prefix and the ideal extension of what the machine translation system has in mind, you basically have a sentence pair that can be fed into an alignment algorithm, and then you can get the word alignments. So some kind of qualitative feedback on this approach. So generally, we find that users like this interactive machine translation. So if you do surveys, that generally most of them actually think this is better than post-editing. But we also found studies, although they liked it, they sometimes are slower than post-editing. More on these kind of studies in a little bit. They had all these kind of word alignment features. So this add cursor word alignment that I showed here, they didn't like so much. And then there's another feature where you can actually go with a mouse over your sentence and it highlights things in the input. So I think the general feedback from users is sometimes contradictory. So for instance, they claim that they like and they think they're faster with interactive MT, although they're slower, or they really hate post editing, but they're really better with it. And then there's also personal disagreements and tastes. There's also a big problem of if you throw these kind of tools at unsuspecting translators, they might see this for the first time and they may not be used to it, and then just because of that are more hesitant of using it. Okay, before we get into user studies, first let's look at how things changed with neural machine translation. So if we do what we just did, this interactive translation prediction, but now with neural magic. So how does this look like in a neural machine translation model? So what a neural machine translation model does, it takes a sequence of already produced output words and the input vector over words and produces the next output word. So usually we feed in as the previous output words the previous model predictions. So in our scenario, however, we can just feed in the user prefix as the output conditioning here. So we just feed in the user input as the prefix and then let the model make additional predictions for the next word. So here's actually a nice illustration how this works on a real example. So here's the input sentence. So a fairly long German sentence. Das Unternehmen sagte, dass in diesem Monat mit Bewerbungsgesprächen beginnen wird und die Mitarbeiterzahl von Oktober bis Dezember steigt. Okay, whatever that means. Point is, here's the predictions of the machine translation system, and this is what the professional translator might accept. So here, the machine translation system was predicting the translator says, yeah, that's fine. I'm fine with that. A set and so on. Basically, the beginning is all fine. And then here it becomes a little bit different. So here it starts talking about job interviews. The company said it will start. And the machine translation system thinks, probably something like job interviews. However, the professional translators decided to say interviewing. So this is also byte pair encoding happening here. And okay, so it starts with inter. The machine translation system is very confused for that and proposes state, so interstate, which is completely off topic. But then interviewing, so it will start interviewing. Now the machine translation system says talks, which is also wrong. So here now the professional translator puts in applicants, but then after that the machine translation system recovers. It says this month, and this is also what the machine translation system, uh, uh, yeah, what the professional translators agrees with. And we kind of see further kind of mismatches. So here the machine translation system says and, but the translator tries to phrase it differently, puts a comma there. The machine translation system still thinks and is a good word there, but the translator says with, but then they agree on staff and so on and so on. So you can see how in the highlighting here is also where the word that the translator chooses is in the prediction. So here when the translator, for instance, predicted comma, yeah, we also predicted that to some, but we were much more sure about and. One more comment on this. This is actually not a real human interacting with machine translation. We just kind of fed in the reference translation as a stand-in for the professional humans translation. So this is our user study we did with neural interactive machine translation. So we compared it against phrase-based MT. We kind of had an interesting setup where we actually had a phrase-based machine translation system that had the same quality in terms of blue score as a neural machine translation system. And we can then measure how good were the predictions. So we just basically measured here on this chart how many X's do we have, how many check marks do we have. And our phrase-based system had only 43.3% accuracy in word prediction, while the neural system had 61.8. So this is without running neural MT without beam search. If we have a beam search of 12, we get better blue scores, and we also get better word prediction accuracy. We also got a report here on letter prediction accuracy. The tool was actually smart enough when you typed in, for instance, L, and then there would be a word that starts with L, it would just predict a word that starts with L, and you would, if you find with that, you can press tab to accept that completion. Here's an interesting analysis of this. So one thing that neural systems were much better at was recovering from failure. So the phrase-based system where we do this lattice match, often after it proposed a word that was not accepted by the translators, it had a harder time to then come up with suggestions that were accepted by the translators. So how to read this table here on this chart here is we just made a mistake. We just predicted a word that the user didn't like. Then we predict the next word that the user like it. And what we have here is, well, for the phrase-based system, the user really still didn't like it. While for most words, the neural system actually proposed the right word. So the word after that, how often did we predict it correctly? And so this is kind of then reverting to kind of the mean prediction accuracy. But it takes a little bit longer. So it really just peaks here after 5 words, while this one already here is pretty much where it should be at the second word. So one interesting analysis here is also that how well we can recover from the user choosing a different word than we had in mind is how likely that word that the user chose would have been predicted by the system. So here in different colors, in blue is if the user chooses a word that we just gave 0 to 1% probability, a word that we really did not expect. This is where then we also had a hard time predicting the next word. But if we give it, if it was a word that was given any kind of reasonable probability, you kind of already here in this 60% range. Okay, some more technical details. So this is interactive. So we have to respond to the translator in real time. So if you use this tool and you press a key, you want to have a response quickly. How quickly? In user interface design, there is kind of this number of 100 milliseconds. So a tool has to respond in 100 milliseconds, otherwise it appears sluggish. However, this is our decoding speeds. So this is on CPU, on GPU. This is numbers maybe that changed with newer GPUs and maybe also with faster CPUs. But here, 100 milliseconds per word, 7 milliseconds per word. So on CPU, we're just not fast enough. You can't predict these words fast enough. So we really have to run this on GPU. But even GPU 7 milliseconds per word, well, then means we can only really predict a few words ahead. So the idea here is, how can we fix this? What if it's a 50-word sentence? It takes us 7 milliseconds per word to translate it. That would be, uh, like a third of a second. That's too slow. So how can we still provide something to the user? The idea here is that we only predict a few words ahead. So we're not going to show the full sentence to the translator anyway. So why don't we just translate 5 words and then show those to the translator? So that then still is within our speed limit. Another idea is to then maybe in the background run the completion and have the full sentence prediction in the background while the user looks at it, or to patch this prediction with any kind of previous prediction we might have had. Some more technical details on this. So if we do this here, we actually lose a little bit in quality. Okay, let's move on to a different topic. Other ways to basically help translators in their work, which I call here choices, because we basically show the translator different translation choices that might be useful. So here we really just show them possible translations for words and phrases in the input sentence, and just for the translator to look at. There's one version of a tool we built where the user can then click on all these phrases and then basically translate by kind of a clicking user interface. What's done also in this tool is here a little bit the more probable translations, like here a lecture, are shown in a bolder or brighter color than the less likely translations. They're also sorted. So they're ranked and color highlighted by the probability of each translation. So why is this actually a useful thing to do? So this brings up the discussion of active and passive vocabulary. If you write text, you use your active vocabulary, words you can think of to put into sentences. This active vocabulary is quite a bit smaller than your passive vocabulary. These are all the words that if you would read them in a text, you would understand them. But these are not words you would think of when you author text yourself. So think about it. There's all kinds of obscure words that if you read them, you kind of say, oh yeah, I know what you're talking about, but these are not words you would use or confidently even retrieve from your memory. But if you show them, in this case, things like a lecture, presentation, a speech, maybe you only thought of one of them, and now we're showing you multiple ones. So now you actually can use maybe better words that you haven't thought of during authoring. I don't know how often it happens to you when you write a text that you feel like, yeah, there's a good word I could use here. I just can't think of it. Here, that word is shown to you. So here's the ranking of the list. So it's mostly ranked by probability of each translation. What we could also do in this list is prefer diversity. So there's a lot of months here. Well, I guess there's not really any alternative there. But here you have planned, planned, planned. Maybe that's a bit too much. Maybe you should have some more diversity as it is here. Here's another feature that might be useful. And maybe that's not just for translators, maybe for any kind of text authoring. So here's the translation. So you already have this translation, but then you look at this and say like, I don't like this give a lecture here. Can you give me alternatives? So can you rephrase that? And then the tool should give you all these different alternative translations here. And then you can pick them. Here's another interesting tool. So this is something that translators actually have been using for a while, which is basically just looking up how a word was translated in existing text. So often you have two choices how to translate something, and you don't know which one is a better one to use. And might depend on the context. So you want to see some examples how the one translation was used and how the other translation was used. So we're looking here at the English here, inter alia, which was apparently translated in two very different ways, about equal probability into French. And then this tool here retrieves all these sentences where it was translated into entre autres, and here it was translated into non talament. I'm totally mispronouncing this, by the way. And then you can look at these translations and say like, oh yeah, actually, I really think this is kind of the better use of the word. Okay, so we introduced a number of tools. We already had a little bit user studies on post-editing at the very beginning, where we showed that better machine translation quality allows translators to be more productive and make fewer mistakes. Let's look now at user studies of translators using these interactive translation tools. So what you need is in your tool do all kinds of logging. So this was probably a useful thing to do. So when a translator uses this tool, we want to know how they use this tool. So in the tool we built, we have various logging tools that check pretty much everything a translator does. Kind of just generally, what configuration the tool was being used, what features were turned on and on, like when was the session started, when was it stopped, when was a particular sentence being started to work with and finished. Keystrokes, mouse events, scrolling of the screen. It's a web-based interface, resizing, search and replace, and so on and so on. What the predictions was of the tool, and even the connection with the eye tracker. So where did they look at the screen? Obviously, this requires special hardware installed with the user. So we basically save in each for each event. We save what type of event, when was it produced, what was produced, and where was it produced, and when it was produced, and also various other attributes. For instance, if some text was edited, how was the text edited, where's the current cursor position, what's characters being looked at, and so on and so on. So with all this logging, it's actually possible to fully replay a user session. Here's one example of actually one of the earlier tools we built here, where we just logging keystrokes. So here's a time axis, starts at 0 seconds, 5 seconds, 10 seconds, 15 seconds, and so on. And a black is a regular keystroke. And purple is pressing deletion, the deletion key. And gray are keystrokes that deal with cursor movements. So what happened here? For first 3 seconds, nothing happened. The translator was reading this French input sentence. And then the translator started typing away. A relatively kind of decent pace for 7 seconds, but then a pause. And then some of the stuff that the translator typed at this moment, the translator deleted again. Some kind of cursor movement, some more typing, some more deletion, but then like an extended period of typing. By the way, the length of this line is the length of the sentence at that point of time. So whenever you delete, it goes shorter. Whenever you type, it gets bigger. And yeah, a little bit of a pause here and so on. So this is the log you have. You can actually then track back how was it typed, when was pauses made, and so on. In this user study, we're also going to talk about quality. I just want to give you some examples of quality judgments which highlight a lot of things. And this is one of my favorite slides. It first of all highlights that different translators come up with different translations. That's not total news. What is maybe reinforces this kind of observation is that even when they're assisted by a machine translation tool, which prompts them and pushes them towards particular translations, they still come up with different translations. So even if you prompt them in one direction, they still manage, all of them come up with different translations. So these are the different translations shown here, and these are the different tools, features they used when translated. So it starts with translation from scratch. So this is unassisted. This is classic post-editing. This is the interactive translation prediction that we first looked at. And this is the display of translation options that also could be clicked on. And then there was also a version of the tool where this interactive translation prediction was a possibility, and these options to click on was also a possibility. These translator L2 and L1 are either they're native. If they're L1, they're native in the foreign language, or they're native in, if they're L2, they're native in the target language. Ideally, translators should be native in the target language when they translate. Okay, so you have all these different translations. We were mostly interested here in the study, and we'll report on that, is when users use these tools, are they actually accurate and perfect and do the right translations? So yet then human judges evaluating them. And here's what the judges say. So they think, for instance, this translation here, without getting flustered, he showed himself to be concise and precise. Four judges thought that was great. 0 judges thought it was wrong. Generally, translators seem to be rather negative in their judgments. Also quite inconsistent. So he showed himself concise to precise. So the hard part is this stuff here at the beginning that MT says without dismantle, which is definitely not great. Here's some translator try to fix that without dismantling himself, which one judge thought was okay, but 3 judges thought it was terrible. Here the whole thing was just dropped. Still, 2 judges thought it was okay, and 2 thought that was terrible. So you have very inconsistent judgments and generally a bit too negative judgments, but that's my subjective view on this. Anyway, these are the judgments we're going to talk about. So later when you see that number of sentences judged to be correct is rather low, here you see an example for that. Okay, here's the results of the study where different translators were using these different options. This is how fast they were unassisted, 4.4 seconds per word. And a little bit less than half of the sentences were judged as correct. Here, they were the fastest with post-editing. They were a little bit slower with prediction. They were even slower with the options. And if they had both prediction options, somewhere in the middle, but yeah, they were definitely the slowest unassisted. Quality generally went up when assisted, although not all that much. Here is actually a breakdown of the different translators, which again illuminates the point that different translators do different things with these tools. And some benefit from tools and some not. So any green box here is when translators that used one of these modalities were both faster and higher quality. A red box is they were both slower and worse quality, and the white boxes are somewhere in between. So there's some translators here that really benefited with any kind of tools, and some translators, no matter what you gave them, it didn't help them or even made things worse. So one big question was, how does it make translators faster? Which is the main objective we have. The quality differences don't seem to be very much, but speed differences are quite significant. So this is how much time they spend when they just do unassisted translation. So these are all translators. I'm saying here novice translators. These were actually students who were fluent in both languages, not professionally trained translators. And they were just basically translating from scratch. This is how much time they spent typing. This is how much time they spent on pauses. So we basically, whenever there was a typing break of more than 2 seconds, we consider that a pause, and this is checking if there was a typing break at the beginning of the translation and how long it was. This is then broken down in over all the sentences in how many seconds per word. Here is then short, medium, and long pauses. So short pauses less than 6 seconds. Medium pauses are between 6 and 60 seconds, and long pauses are pauses longer than a minute. So what you see is that the slow translators are slow, not because they type slow, but because they have a lot of thinking about the translation. So they have a lot of pauses longer than 6 seconds. Here's the fastest translator. Yeah, he types definitely fast, but not extremely fast. But the big difference is very, very few long pauses. Here's one particular translator. So this is now a native French translator. So we're doing French-English. So he knows the source language really well, the target language. These were actually all students at the University of Edinburgh. So they studied in an English-speaking country. So they were also fluent in English enough to study at a university. So what do we observe? When we give them the different tools, so here's unassisted, this is the baseline. If we give them all these different aids, post-editing, option, prediction, or both prediction option, they spend less time typing. With the options, they do spend some time typing and clicking, but if you just add these, even if you add these numbers up, you're much less than here at with keystrokes typing unassisted. So they spend less time on typing, and they spend less time in having pauses. So this is the initial pause, which is for post-editing, still about the same, but for the other modalities, quite a bit less. Not much difference here. The biggest difference is really these big pauses. So there were a lot of time spent in these long pauses, which then was significantly reduced. Okay, let's look at another topic, which is confidence. And here we're talking about confidence metrics that could be provided to the user. So we basically want to come up with a method where a machine translation system knows that it's probably wrong and wants to communicate that to the user. So the basic idea here is if the machine translation system just is not very confident about its translation, thinks this is a rubbish translation and producing here, maybe don't even show that to the user. So this task of the machine translation system while translating, also providing a confidence score, is also called quality estimation. Lucia Spezia is a researcher who's done a lot of work in this area. There are different levels of granularity. We might want to have that. So we maybe when a machine translation system produces a document, we want to say this is a well-translated document. So SDL, a company that's been working on machine translation, developed a metric like this called trust score. They actually used it. A famous example was translation of restaurant and hotel reviews. you don't need to translate all the hotel reviews. So maybe if there's some hotel reviews you can't translate very well, don't show them to the user. Only show them the translations that are actually translated well. So that's document level, sentence level, word level. And then the question is, what are we predicting? So here's an idea. Maybe you should just check if a translation is good enough for post-editing and have people assess that. People did that. So can you assess a translation on a scale from 1 to 5, how useful the translation is? Maybe you just want to know, yes, no, is this translation good enough that post-editing is worthwhile? Another thing that might be interesting is figuring out how much time it will take to post-edit this. So if you could do this, if you could estimate how much effort it would take to post-edit, then you can actually check for a big translation project. Okay, this translation project requires 15 hours of post-editing efforts. This is then how much I'm gonna pay the translator. And maybe we also want to be a bit more fine in granularity and pinpoint errors. So if we produce a translation, we also want to say, well, words 3 and 4 are a bit shaky. The rest are pretty good. So translators are actually already used to something like that in their translation memory tools that I talked about. So when a machine translation system, when their computer-aided translation tool retrieved the prior translation, it retrieved this prior translation with a fuzzy match score. So how similar is the input to the input that was retrieved? And this is called the fuzzy match score. And they know if there's a fuzzy match retrieved that's not very good, it's not worth looking at it. So their threshold is something like maybe 70%. If the difference in the similarity between the sentence I have to translate right now and the sentence retrieved is less than 70%, it's not bothering looking at it. So it would be nice to have a similar score for machine translation. So, but even better, we would like to estimate maybe post-editing time. We might like to know how much time would it translate this from scratch and then use that in pricing. So this is an active research question. This whole topic of confidence scores is a big challenging problem still for the field, and it hasn't really gotten much better. So what do we do with this? So one idea is word level confidence. So what if this is the input sentence here, and this is a machine translation? We now want to highlight which words we probably have mistakes with. So we kind of underline here in red, well, that's probably a bit shaky. And then in green, well, we're still not entirely sure about these two words. So this just basically highlights words that are maybe wrong, and maybe words that should be reordered, should be placed in a different place. But it's kind of hard to highlight missing words. We can't say, well, maybe there should be another word in here. Finally, and kind of in the same vein, we might also want to come up with methods that do automatic reviewing. So we talked a lot about errors in machine translation and how we can improve our machine translation system and so on. But we also have professional human translators who might also make mistakes. So there are particular types of mistakes we might actually have some hope of detecting automatically. So what if the translator, while they translated, missed some of the content or added some additional information that was actually not in the source? That's something we might be able to detect. Another one is inconsistent use of terminology. What if there's a foreign word that occurs multiple times, but the translator then chooses to translate it differently? That's probably not the right thing to do. So this is what we have in mind here. If this is the input sentence and this is the human translation, we would like to spot that the translator added this here and this here was not translated during translation. So how can we do this? Maybe we can do word alignment and so on. This is a pretty open challenge still. So you basically try to be smarter than a human translator, which is kind of a high threshold to clear. Okay, final topic I want to talk about is adaptation. So we already had an entire lecture on adaptation. Let's just kind of discuss a little bit how adaptation comes up in the context of computer-aided translation. So we already discussed that machine translation works best if it is optimized for a particular domain. And we have the problem that typically large amounts of out-of-domain data is available. So European Parliament, United Nations, some web crawl data, but there's only very little in-domain data. Maybe we only really want to build a machine translation system for information technology, or maybe even more specifically, my translation job that I have to deal with is IBM user manuals. So how many IBM user manuals do I have? And ideally, actually, I want to have the IBM user manual for the same product line from last year, or even better, I'm in the middle of the translation project. I already translated some sentences. These sentences are probably the most evident, best evidence for how I want this stuff to be translated. But that's going to be very, very few sentences at this point. So we already discussed domain adaptation techniques to deal with that. Here is now the specific setup for computer-aided translation. So source text comes in, we have our MT engine, translate that, we have the machine translation. We then have the humans post-edit it and have the human translation. So with that human translation in mind, we would now, and paired with the source sentence, we now have a sentence pair that we actually would like to feed in back into the machine translation engine. So we want to like to improve the machine translation on the fly with sentences that come in from the human translator. So while the human translator is translating, we want the machine translation system to incrementally update. So in statistical machine translation, one big solution to that was to store the corpus in memory, so don't actually build a phrase table and all that on run word alignment offline. We just store the corpus with actually word alignments in memory, and then when we can add a new sentence pair to the corpus, all we have to do is add a sentence pair to the corpus, attach it to that list that's in memory, and then have an index data structure, so-called suffix array, that allows quick lookup of translations. That turned out to be actually a quite quick and efficient way of doing things. And this allows us to then add new sentence pairs at a time because the translations are regenerated. The translation probabilities and options are regenerated each time on the fly when a new sentence is being translated. The answer neural machine translation is fine-tuning. There's all kinds of special handling of words. There's a lot of ongoing research in this area, and we already discussed some of it in our lecture on adaptation. Okay, that's it for today. So we talked about the use of machine translation in the translation industry. This is becoming increasingly standard. So there was for many years big uproar about how machine translation is not really helpful and terrible and not useful. And then basically we are at the point. And then there was a long phase of translation agency managers pushing machine translation. Actual translators hated it and they said, you give us crappy MT and pay us less, make our life miserable, and now it's become to the point of being inevitable, and post-editing is being recognized as a skill, for instance, in addition to just raw translation. However, how to do best the interaction between and humans is still an open problem. There's actually not very much research in this area. So we had a research project about 5 years ago, until 5 years ago, called Casmacut. There's actually an open source toolkit you can download and install it on your machine. You can actually have the entire thing running on a laptop. This is still operating on statistical MT models. We've done some research on neural MT, but this particular toolkit is only using statistical MT. You can actually try it out and play with it. So I really encourage you, if you're interested in this area, there's interesting work to be done. Okay, and that's it for today. And this is actually the final lecture of the course, so I'm glad you made it all the way up to here.